This tweet of mine mocking GitHub's safe sleep implementation made rounds on Twitter recently, and people in the comments been speculating that maybe, GitHub didn't want to rely on a sleep binary that Linux distributions usually ship, but instead have something portable, and they decided to use this abomination that first busy waits instead of sleeping, and second it relies on the bash magic variable that uses a system clock, which can be adjusted at any moment due to daylight savings or just due to some kind of a drift, and also it can skip a bit. Whatever, this is very unreliable. So I figured maybe let's learn something today and implement a fully standalone, from scratch, sleep implementation that has only one dependency on Linux, the kernel itself. Here is our starting point, the very basic sleep implementation in C programming language. I'm using C just because it's the most easily accessible. GCC is installed on every possible Linux machine, and it's easier to follow along, but it's not any different for any language that compiles to native code and has access to Linux kernel system calls. Let's compile it. Let's see that it only depends on libc. Let's make sure that it works. So sleep without any arguments prints usage, and if we give it a number, it will print this number and sleep with this number. I don't know if you saw it, but yeah, it actually sleeps. And if you look at an actual implementation, it's very simple, just some sanity check for argument counts, printf usage, A2L usage that parses a raw string into number that we get from the command line arguments. Then we print in this number and we pass it to sleep, which is a libc standard function. And now what we're gonna do is we're gonna strip these dependencies, rewrite them one by one until our application does not depend on libc at all. The greatest thing about compiled languages is that the compiler can guide you. So if you take our compiler and you just pass a no stdlib into it, the entire thing breaks. So this flag in GCC tells it to not link against libc, and it instantly tells us what we need to rewrite. So we don't have something named start. We don't have something named put as, A2L, printf, and of course sleep. We're gonna start rewriting A2L because it's the most standalone thing and probably the one that is easier to rewrite at the moment. And I can't actually stomach this libc A2L name. Why is it even called A2L? I don't think at this point anybody knows, so I'll just call it parse int. And what it accepts char star row number. Let's call it row int. And how do we structure it? So we have a result, which is 0 at the start, and at the end we will return this result. We also want to track our raw integer with something like char star cursor, which is raw int at the start, and then while the cursor, which we will need to constantly dereference. Dereference cursor is between a ASCII character for 0 and cursor less than ASCII character for 9. So what we need to do is, keyboard, help me. So what we need to do is we need to take our result and add it, the previous result times 10, and plus we need to get a number under the cursor. In order to get it, we need to get the cursor value and subtract an ASCII character for 0. So ASCII character for 0 is 48, ASCII character for 1 is 49, and so you can imagine if this has ASCII character for 2, so 50, 50 minus 48 is 2, so 2 the number. Yeah, makes sense, makes sense. And at the end, we of course need to bump the cursor, otherwise we enter an infinite loop. So let's check if it works. Parse int, and let's actually compile it with the libc again and run it. So it works like that. And then if we provide 5, yeah, sleeping for 5 seconds, give it 2, sleeping for 2 seconds. Yeah, seems like our implementation is still fine. And I should probably disclaim right away, so we are not going to cover all possible original sleep parameters. As you might know, the sleep binary, it also accepts floating points, and it also accepts infinity, so some ASCII. I'm not gonna parse anything like that, so let's actually reformat it slightly. This is how I like it. Yeah, so making the most robust implementation is not the goal. We're just trying to learn something new here, right? Okay. With disclaimer out of the way, let's compile the thing without libc again, and let's implement something new. For example, actually, let's track the start symbol. And it is an interesting one because if you didn't know, main is not an actual entry point into your program. The actual entry point to your program is called start, and it has a signature of void underscore start that doesn't accept any input arguments. And then this one calls your main with argc and argv that it gets from somewhere. We'll figure it all out. And this is what the compiler, well, actually it is a linker, so the ld is a linker. This is what it refers to when it says it can't find entry symbol start. And when we compile our program normally with stdlib, libc actually inserts the symbol into your executable, and then the linker is able to find it. So let's figure it all out. Let's figure out where start gets those two little bastards. And you know, in the era of LLMs and ChatGPT, is as important as ever to know how to find the initial source of information. And this is what we're gonna do today. And you know, flashbang alert, we're going to be looking at System 5 application binary interface. And I guess if you haven't figured it out yet, our example today is going to be for AMD 64 machines. So x86 64 processor architecture, simply because that's the computer I have here. So that's what I'm gonna be writing. Oftentimes, these kind of manuals, you know, low-level nitty-gritty details, they have this reputation of being very hard to approach. But what I actually find is they often are very precise and very, you know, easy to get into. So for example, here we need to find how the entry points start getting structured. And I can literally just search for start, and you see it's the only match. And if you scroll a little bit above, the chapter literally called process initialization. And if we scroll a little bit under the stack state, we can read it. For example, a C program begins executing at function named main, declared as extern int main argc and there's also a third one which is environment variables. We are not gonna care about environment variables, but just so you know, they're also there. Anyway, so argc is a non-negative argument count, our argc. argv is an array of argument strings with argv, so the last one being null terminator, and then environment variable we don't care about. So when main returns, its value is passed to exit, which is the system call. What we need to look at is the initial process stack. So we have some kind of undefined low address. Then we have our argument count, which is argc, and it is located at something is called RSP, which is the register that holds the stack pointer. Then after 8 bytes, we have our argument pointers, and everything after that we don't really care about. Another thing, and oh yeah, right. So look at this. It also says that we have something called RBP, that content of this register is unspecified at process initialization time, but the user code should mark the deepest stack frame by setting the frame pointer to 0. So we are going to be doing that. And our RSP, the stack pointer, holds the address of the byte with lowest address, which is a part of the stack. So you guessed it, we are going to write an assembly inside of our C program to get all of this information. So let me clear the terminal because my head will obscure what we're gonna write. And let's start on the inline assembly, I guess. And you saw that everything argc, argv gets calculated from the stack pointer. So you can imagine a naive way of writing the start as something like, we try to capture RSP in assembly, and the way you do inline assembly is you do asm like volatile, something like this with double underscore. And here you write it as a string, so like move RSP into the output parameter. And this, I guess I need to apologize that GCC by default uses something that's called AT&T assembly syntax. That is horrible. I hate it, but it is what it is. If you ever saw normal assembly, you know that these are swapped, and also these horrible percent signs that they're very confusing. But what you need to know is that if you're using input or output arguments, you need to prepend them with percent, and then you need to prepend an actual literal registers with double percent. And then to capture an output variable, you put a colon and set equals R and RSP. And this refers to this RSP, which tells GCC to capture the value that is at the RSP register into this variable. And yeah, by the way, this is long. This is all in 64 bits. And what you do next, you declare argc, which you get by casting this thing to a pointer and then dereferencing it. So like a long pointer RSP, and then yeah, dereference this guy, and then you have character star star RB, which you also do like this. So you cast something to a character pointer, but it should be RSP plus 8 plus 8. Just to reiterate, RSP contains an address of argc, and everything else kind of gets calculated from it. After that, well, I probably need to, cast argc to int here before I pass it. And now if we compile it, we can see that linker doesn't complain about start anymore. It only complains about other symbols. So let's make it work back. What I'm gonna do is I'm gonna keep using nostdlib, but I am still gonna link with libc explicitly. So what it does, it will let me use these functions, but it will let me control the entry point. So if I do this, it still compiles, and if I try to run it, it print the usage and then segfolds, which we're gonna do later. But if I now provide an argument, so yeah, what is going on? Why argc and argv don't work? Let's actually print them. So argc is %d and argv, I guess let's print the first one is gonna be a string. And let's maybe print argv, the second one, which is also a string, and argc, argv0, argv1. Let's see what is going on. Let's recompile and let's rerun. And what is this? This is clearly some garbage, right? So if we run it multiple times, you see that this is just doesn't look good, right? So what is going on here? And what is going on here is that the compiler actually moved RSP before we get chance to access it. So let me show it to you. There is a program called dump, and it has a -d argument which calls a disassembler, and if we call it on our sleep executable, it has a bunch of code, but at the very bottom we see our start, and the start with push RBP and then move RSP RBP. So you can see that compiler is messing us up. It inserts some bullshit code into our executable before we are able to get the argc from the stack pointer. This is where our inline assembly starts. So move RSP to racks is this part, but there's something before it. So by the time we're trying to access argument count, the stack pointer already moved, so we get garbage. And so how do we avoid it? And well, here's how. This bullshitted compiler inserted into our start is actually called prolog, and it does it really before any function call. So we need to get rid of it. And the way you get rid of it is you explicitly tell the compiler to stop doing that, to make your function naked. This is an actual term. Sorry, I bumped my microphone. The way you do it is you prepend your function with an attribute, and in double nested paren you say naked. So when you do this, compiler is not gonna insert any prelude anymore, but as a, I guess, payment for that, you need to write pretty much the entire thing in inline assembly. So this is what we're going to do. Let's remove the C code and let's write everything in this start entry point as volatile. And as you actually might still remember, in our guide, the first thing about the stack kind of state says that we need to mark the DP stack frame by setting frame pointer to 0. And the way you do it in assembly is, well, the way people do it is they just XOR RBP with each other. And RBP, RBP. This effectively zeroes this out. And you know, there's even a sort of small optimization. People usually replace RBP with EBP because, you know, it's something like it refers to 32-bit register. It saves some like cycles on encoding and decoding instruction, but it still ends up zeroing the register out. So this is just some optimization that people who write manual assembly do. Next, we need to somehow get these arguments and then call main with them. So, and how do you do this in assembly? So we need to know registers to which we put stuff from RSP before we call main. And again, our System 5 manual will help us. If we scroll a little bit up, passing. So here it is. We are in the section that discusses passing arguments to the functions. So the section is called, parameter passing, right? It says something about classification, blah, blah, blah. But anyway, so passing of integers. So we know that both of our arguments here, argc and argv, they are integers because this is an actual integer. And this is a pointer to an array of strings, and pointers are integers. The way you pass an integer is you pass them, the first argument goes to the RDI register, the second one goes to the RSI register, and this is what we need to do. So let me clear that up, and let me copy paste this, and so we move in whatever is in RSP. So I am wrapping this in parentheses to load a value on an address that is on the RSP register, because as you remember, the way we read it in the manual, RSP doesn't contain the argc itself, it contains the address of that thing. And so we're moving that to, what was it again? To RDI. Yeah, to RDI. And after that, we move in whatever is at RSP plus 8 to RSI. And to get the relative address, you use another instruction. It's called LEA, which is load effective address of RSP, but offsetted by 8. And this is how you write it in a TST syntax. After that, you can call main, but, well, yeah, you can call main, but actually not quite. Not quite, because we read here that, you know, the stack is guaranteed to be 16-byte aligned at process entry, but after that, it's our job to keep it aligned, because we kind of told our compiler to not do it to not do anything with our assembly. So What we need is we need to make sure that the stack is aligned, and to do that you just literally add RSP with some number that ensures the alignment. And this is how you do constants. You say -16, which is like just a fancy way, because you know, two's complement, sign extended, blah blah blah, to write a number that looks like 0x and, you know, 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8. So this is just a fancy way to write this number that has everything set to 1 but the last 4 bits, and when you mask it against RSP, becomes, you know, divisible by well, by 4. So yeah, or a multiplier of 16, I guess. And now it is aligned, and now we can call main. And let's recompile our executable. It compiles, and now we call it. Hey, look at this. We have argc, which is 1, and we have argv0, which is sleep, the number of executables, so it's actually correct. And then if we provide something like, you know, 2, we would print the usage right before we. So provide 2, we have sleep and 2, and we actually slept. Look at this. So our start entry point, it seems like it's working. Well, it works apart from the fact that our executable has some illegal instruction, crashes at the end. What does it mean? Well, you might see that main actually returns something, and this something is an exit code. And in our start, we never call exit. So let's be a good citizen and set the correct exit code before our start ends. And we already know that to call something, we have to put the input argument, the exit code, to the RDI register. But you know, where do we get it from? We need to know to which register this 0 comes as an output, or I guess return value of main. And we can again reference our manual. And if we scroll it all the way up, this is the passing section and returning values. If the class is integer, the next available register of the sequence rax rdx is used. So we know that rax is not used. So the 0 that our main, or I guess 1 in this case, if we just print the usage, it's gonna be on rax. So what we do is we move whatever is in rax, we move it to RDI. And after that, we are going to call exit just straight up from libc. And let's recompile and run our sleep without any parameters. And you see that it doesn't crash now, and it actually says the correct exit code, which our shell happily displays. And so if I set it to 5, it should sleep for 5 seconds and set the exit status to 0. Hey, look at that. It works. So now our start entry point is just fine, and we can keep rewriting. So let's recompile our executable without linking against libc and see what breaks. So no complaints about start anymore, but we have undefined reference to exit now. So I guess let's tackle that next. And this is where we finally get into implementing a syscall from scratch. On Linux, there are syscalls. Syscalls is some binary interfaces between your user space program and the kernel. For example, if you want to exit from your program, you call the exit system call, providing an exit code, and then kernel terminates your program with that exit code. So how do we do it? Well, we are calling exit, which is a function. So let's write it. And exit has like a void, and it accepts int. Let's actually call it long, because everything here is a 64-bit, right? So exit code, and we need to call some kind of assembly here and pass everything into right registers. So how we do that? Surprisingly enough, the answer is in the same exact manual. So there is a special section for AMD64 Linux kernel conventions. And well, here it is. User level applications use integer register for passing RDI RSI. We know that. And the kernel interface uses RDI, RSI, RDX, blah, 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 right? So they're actually very similar. And the system call is done via the syscall instruction. And then the kernel destroys these registers. And the number of the syscall, so for example, exit needs to get passed on rax. And then rax also gets the return result, which can be either an error or an actual value. So with this information, let's go and implement this assembly. The convention on Linux is to have like a function per syscall, and for example, you call syscall syscall1 if it only accepts one argument, syscall2 if it accepts two arguments, syscall3 if it accepts three arguments, and up to six, right? So exit accepts only one argument, so let's implement that. So the syscall will accept the number of a syscall. In our case, define sys. So I'm just kind of following the libc naming convention, and sys exit in x86-64 architecture has a number 60. I just kind of know that because I am prepared. And then we have an argument, so syscall1 only accept one of them. And so it has a result of a syscall. Exit doesn't need a result, but in general sense it has. And after that, we can start writing assembly. It's again volatile. So what do we write here? As the spec said, we need to call syscall instruction, and that's literally it. The complexity here is in specifying what registers get input and output. First thing that we do is we specify the output. Return from syscall goes into the rax, and the way you specify rax is you say equals a, like this, and you set it to result. Then you need to provide input register. This is actually something new. And yeah, rax again, rax as an input without equal sign. So here goes the number, and then capital D, which is RDI, is for arg1. And then, so here, so yeah, RDI. So capital D is for RDI. And then you need to say what registers the syscall destroys. In our case, syscall destroys RCX register. And in this case, it's actually without percent sign because, AT&T syntax is weird. Also R11. And also, this is not something the spec specifies, but you always need to add a memory here, because the rule of syscall is that the kernel can modify any memory in your executable at any moment when you switch control to it. So you need to tell the compiler that it needs to read from memory after syscall is done. And so after we do all of that, we can return result. And now we should be able to call this in exit. So just call syscall1, provided sys exit as a call, and code as well the code. And let's see if I actually did it all right. So let's compile. So what do we have here? Conflicting types for exit. Oh yeah, it's because I am still including stdlib. I don't think I even need it anymore. Nice. So what do we have? Expected void int. So this is just compiler knowing signatures for built-in functions. So let's, remove this warning by accepting the code as int. And now what do we have here? We actually sort of compiled, but there's a warning, no return function does return. And this is kind of an annoying one. GCC knows that exit should never return, but it can't detect that we don't return actually here. So just to make it shut up, I don't know, we just add an infinite loop here at the very end, right? And now it doesn't complain about exit anymore. So let's actually compile against libc again, just to make it work and see if this all works. Yes, so colon sleep without arguments sets the exit status as 0, and then sleeping for something, for example, for 0 seconds, sets it to 0. Nice, so we all good. This works, and let's, I guess, move all of this at the top of our program. So all syscalls are going to live here, and syscalls numbers are going to live on top. So now we have syscall that accepts a one argument. Nice. So what do we have next? Let's again recompile it without libc and look at the next target to implement. And seems like the only thing we have is printf. And implementing printf as it is in libc would be super annoying because, you know, it accepts all of these formatting parameters. By the way, let's remove this debug output. We don't need it anymore. So we are going to implement a very simple, just a regular print that just prints string to std out, and that's it. So let's draft it. It's gonna be probably void print, and it's going to accept a string to print, and it's gonna be character star string. Yes, and so the way you actually print to the console in Linux kernel is by using the write syscall. And so yeah, write, and if you look at the manual for write to a file descriptor, it accepts a file descriptor, which for stdout is 1. It accepts the buffer that we print from, and it also accepts the size of the buffer. And you can kind of count 1, 2, 3. So the internal syscall accepts 3 arguments, which means that before we proceed, we need the version of this, but with 3 at the end. So let's copy that. Let's change to 3, and let's add long arg2, long arg3. So you could kind of see that syscalls in Linux, they are additive. So the syscall 2 would build on syscall 1, and syscall 3 would build on syscall 2. And let's look up the registers again. It is RDI, RSI, RDX, R10. Yeah, right. So RDI is capital D, then RSI is capital S. This is arg2. And then actually lowercase d is for arg3. And by the way, how do you know all of these mnemonics? The answer is, again, from the first principles. You go and read GCC manual. It has for x86 family, it has all of them. So A is the A register, the RAX or EX in 32-bit. D is the D register, so it's RDX, and then if you do like capital D is DI, so RDI. And yeah, it is a bit weird. It's kind of hard to follow. Again, gonna complain about AT&T syntax, but it is what it is. This is just what GCC has by default. You can use Intel syntax, but you would only be able to use template strings with Intel syntax, not the, so you would only be able to use this with Intel syntax, but the output, input, and clubbered registers should still be in AT&T, at which point, you know, why bother? Anyway, stop complaining. We have our 3 arguments, and everything else is actually staying the same. We have our syscall 3, and now go back to implementing print. And what do we call? We call syscall3. We pass sys right, which is actually right is the very first syscall. Yeah, there you go. And after that, we provide the string buffer itself, which we need to cast to a number. So yeah, the pointer to a string we cast to a number because all of these syscall arguments are, well, longs numbers. And after that, we need a length of the string, which in the libc is strlen, that we pass the string in. And this is called, well, it returns the amount of bytes written, but we are not gonna handle errors, so we just ignore the return value. And I guess we need to implement strlen that since we don't use libc, right? So let's do it right now. Oh, but before we do, yeah, since this is a syscall3, this should also accept a third argument, which is actually the first, and this is the file descriptor, which is stdout. Anyway, so yeah, strlen. strlen and libc has a signature of long unsigned, long unsigned strlen, which accepts character star string. And you implement it in a similar fashion as parsing integer, which is just like a running cursor, the simplest possible implementation. Cursor equals string. And while you just check if the cursor is not a null terminator, so just I'm here and cursor plus plus, just like literally add it to the number. So you add a number to the cursor, which will increase its number. So it holds an address. Every kind of plus adds to the address. And at the end, what you return, so what's going to be like a long unsigned result is going to be the cursor, which at the end of the string should be standing at the null terminator. You subtract string from it, which gives you the length. Right? This is just like the very dumbest, smallest implementation of strlen. Totally production ready. And now this should hopefully work. Well, before we check it, let's change all the printf calls to print. And this one, to avoid the formatting, we actually split it to 3 print calls. I think like this. So let's try it out. Ah, look at this. It doesn't complain about anything. So let's bring alc back and oh, look at this. It works. First try. So printing usage without any arguments. And let's try to sleeping for 5 seconds, sleeping for 2 seconds. Does it still sleep? Yeah, it still sleeps successfully. And I think at this point, we don't need stdio header anymore. And so we are actually only left, as you can see, with sleep itself to implement. Yeah, the last one, the topic of our today's video. And sleep is an interesting one. So there is no syscall that is called sleep. The syscall that libc use under the hood is actually called nanosleep. If we look at it, what does it accept? Well, it accepts 2 time spec structs. So we have a syscall2 to implement. And also it uses exactly what we need. I know for a fact that it uses clock monotonic by default. Which makes it independent from stuff like clock drift and daylight savings. So this is what we need to implement. First of all, this is going to accept 2 arguments, so we can actually get the syscall 3 and copy it and call it syscall 2. Just remove the third argument from here. So again, syscalls are kind of just built on top of each other. This is very, very convenient for us because we can just copy paste. And I also happen to know that syscall nanosleep has a code of 35, right? And if we go at the very bottom, let's implement it on top of main, because this is where it gets used. Sleep is gonna accept seconds, and it's gonna call some sort of so here's where it gets a little bit interesting. Interesting because we looked at the manual, we need some kind of a struct time spec. And so what is this time spec? And it actually comes from the header called time.h. And if we go there and look at the time spec, struct time spec, I think it's here. Yeah. So, and so, nice one. So this is why people hate glibc. Just look at this. It's I I understand that you want to support a lot of different architectures, but and but surely there's a better way to structure it. That this is horrible and unreadable. This is why people get so intimidated at looking at standard library of programming languages. Like shouldn't write it like this. So what I wanted to show is that time spec is essentially a two 64-bit integers, tvsec and tvansec. Let's actually close this horrible thing and define it here. So struct time spec is going to be, it's a long tvsec, and same with tv ansec. Let's actually type def to this little trick is so we don't have to write struct keyword everywhere. Let's close, let's remove time.h, and actually let's remove the last remaining. Whoops, I accidentally closed my Emacs. Very good. And so where were we? Yeah, go back here to sleep, and we need to call some kind of a syscall, which is actually syscall 2, which is sys nano sleep. And then that was a pointer to duration, which should be duration. And then a pointer to rem, which is a remainder. So how long do we still remain? How long do we need to sleep after we got interrupted? We're not gonna cover interrupts here. Just know this, exists. So we're just gonna pass a 0 here. And yeah, we need to initialize duration, which is a time spec duration. And let's actually zero initialize it, right? Because we're in C, we need to do this. And time spec tv sec equals seconds. I'm not gonna handle cases like sleeping for half a second. Know that if you want that, you need to handle tv and sec. We need to pass a pointer to this into the syscall, and so let's cast let's cast time spec to a long before we do that. And wait, this should be the other way. We should take a pointer to a duration and then cast this pointer to a number. We can't cast just a struct to a number, come on. And seems like when I closed my Emacs accidentally, I also nuked the terminal. So let's reopen it back, and let's actually compile it. Oh, look at that. It actually compiled first try. That is some, oh, because I didn't save it yet. Let's try it. So what do we have here? Unexpected identifier, time spec duration. Oh, this is not time spec. This is a duration. Yeah, getting a bit late here on my end. So, and now it compiles, and can we actually run it? So usage sleep number, sleep seconds, and hey, look at this, it works. But now let's compile it without linking against libc. Will it still work? Oh, so what does it tell us? It tells us in function sleep undefined reference to stack check fail. And so this is something that compiler does for us. It makes sure that our stack is all correct and protected. So it inserts stack protector, which we are not gonna concern ourselves with. So we're just going to disable it. And to disable it, you compile with another flag. So I think it's no stack protector. Yes. And so now sleep, so usage, we are sleeping for 2 seconds, and seems like there we have it, a complete independent sleep implementation that only depends on the Linux kernel. So let's actually look at it. And now it is statically linked, even though we did not specify it. The compiler just kind of, figured it out. Since we don't link against anything, we need a statically linked executable. And if we are ls.la, it's gonna be about 14k, 14 kilobytes. If you know your compiler toggles well, you can compile it with size optimizations. You can then strip it, remove all the section from elf binary, which which takes up a lot of this executable size. And you will get it slightly under 10k. It will maybe 8k, but it's not the point. The point is that it's still very small. It's just a couple pages with some padding around it and some executable overhead. You can ship it on a target computer. You can execute it, and it will work on any x64 processor that has Linux installed on it. And if you want if you want ARM, you can literally just re-implement the syscalls with slightly different assembly as well as this entry point, and you will have sleep for another architecture. So this is it, completely standalone, fully independent, future proof, as long as I guess Linus Torvalds is alive and don't break user space rule applies. Executable that is implemented, you can say, from the first principles. Was it hard? I don't know. I don't think so. It just required a little bit of spec reading and a little bit of enduring some inline assembly. But yeah, there you go. What do you think? Leave comments below. Subscribe if you want more stuff like this. Yeah. Bye bye.